Welcome back, everyone. So as the title suggests today, our goal is to answer all the questions, of which I have had many. So I'll answer those questions. I'll leave time for you to ask questions if you want to ask your own questions. And then I'll put the quiz up, and you can go type up the quiz and then turn in the PDF once you are done. Okay. So just a note for Monday. You should view the videos on 3.1, of which I believe there are 2 videos, and then you should start the homework for 3.1. Which ends up being due on Tuesday. Okay. In general, in this course, it's going to behoove you to start homework as soon as you possibly can, because you're going to want to have the time to think about the questions on the homework before you have to turn them in. If you just sit down to do the homework and plan to do it straight through, like you might a calculus assignment or something, it's usually going to go poorly. You want to have time to be able to soak in the questions and think about them, identify what the easy parts and the hard parts are, and give yourself some time to sort of soak into these things. Okay. Now, I fully acknowledge and understand that given that this course is going at double pace, there's a little less room to do that than there normally would be, because we're doing 2 weeks of material in a week. So basically, every class meeting is kind of like a week of class, but give yourself as much time as you can to think about the homework. I always post it early, so you want to be looking over the homework and thinking about it as you watch the videos. Okay, I wanted to make 2 notes that I just wrote to myself before I jump into your questions. Okay. The first note is about working together on homework. You are perfectly welcome to work together on homework. But there's a pretty easy way to know if you are doing something you shouldn't be, which is that you should never be copy-pasting stuff from other people to other people for the homework. Okay. So some of you are clearly turning in the same answers because you typed them up together or whatever. That you should not do. But if you are wanting to work together on solutions and thinking up, what is the idea? How do I do this problem? How do I write this proof? Or if you want to check answers against each other or whatever, that's all well and good and in fact encouraged, because the more you talk about this stuff, the better you'll understand it. But just make sure you're sort of sticking within the bounds. You have to do your own writing. This is a writing course. You can't turn in someone else's writing. Okay. Next up, I wanted to talk a little bit about how important notation is. So there was a question on the homework that was something like, list 3 elements of Q plus, or whatever it was. Okay. So I had people turn in things that looked like this. People turn in things that looked like this. And people turn in things that looked like this. Okay. This is definitely not right. This is a set. Okay. So this is one set that should not be what you're asked or what you're giving when you're asked for a list. Okay. Likewise, this is a tuple of points, so this is something that lives in R3. This is not what you should list either. And so the thing when you're asked for a list, you should give a list that looks like this. Precision is going to be really important in this course when it comes to notation. And it's going to be sort of your life raft to stop yourself from getting confused. Because as soon as you're using the wrong notation for something, it means that you've let yourself get a little bit confused. And once you've let yourself get a little bit confused, then it's pretty easy to get a lot confused. So be super vigilant and make sure you understand what all the symbols you're writing mean. Okay, let me talk through the questions that people have submitted. If questions come up as I'm talking about these things, please drop them in the chat and I will try and address them. So the first question was about the significance of the little proof box. Okay. This just means the proof is over. Okay. It's sort of like a period to end a proof. Okay. Now, if your homework looks like, okay, problem 1, prove blah, okay, and then you say, okay, here's my proof. And then you put a proof box, problem 2. Prove other blah. Okay, blah, 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 blah. Proof box. In this case, these proof boxes are unnecessary, but they're not hurting anything. And in fact, again, if you do this in LaTeX, the most natural way to do this is to put this thing in a proof environment. And as soon as you put something in a proof environment, LaTeX will automatically put a proof box at the end. And as discussed, you can change what symbol LaTeX uses to mark the end of a proof. Okay. However, when you're writing something longer, such as when you're writing a senior paper or a textbook, or maybe your proof has multiple parts, you really want to have proof boxes in order to tell the reader where the proof starts and ends. Okay. Because if you don't do that, then it can be really difficult to figure out where to start reading again when you're reading this. It's just an important part of the grammar of writing these things. Okay. And so if you look at sample math textbook here, you'll see they say, okay, here's the theorem, so here's the thing they're proving, here is the proof, and then at the end there's a proof box, and that is useful to the reader to say, okay, if I only want to understand the theorem and I don't want to look at the proof just now, I can know that I can skip to the end of this, or if I want to focus on the proof of Siegel's theorem, I can look at this piece and figure that out. Okay. So as soon as you're writing something that has sort of more than one piece, you definitely need to have proof boxes. If your homework is just a list of problems with proofs, then maybe you don't need them, but I think you'll get them automatically with LaTeX anyway. Okay. I had a few questions about bipartitions. This going back to this question on the homework that defined bipartition and then had a few questions about it. And I'm happy to talk about those questions specifically, but if you're asking about bipartition specifically, that's not really the right question, because bipartitions are probably not ever going to appear in this class again. The skill that you're practicing with questions like the bipartition question is the skill of reading and understanding definitions. Apologies for the road work that they have decided just now to start doing right outside of my house, by the way. So when I talk about reading and understanding definitions, what I mean is you're often going to encounter on the homework, just like you did in the bipartitions question, a question where the first thing is the definition of something you've never seen before and will probably never see again. Okay? And you have to read the definition, figure out what it is, maybe come up with some examples, and then answer questions based on it. Okay. And you're going to do this a lot because this is, in fact, one of the skills that is most important for math classes you'll take in the future, because you're going to be comprehending lots of definitions. Okay. So for any particular one of these questions, I'm happy in class or office hours to go over what the thing says, But the point isn't for me to tell you, okay, this is what a bipartition is, because you're never going to see the word bipartition again. Rather, the important thing is for you to practice understanding, okay, how can I read the text that is given in the question and understand what this thing is? So I would encourage you, when you're directing questions about these sorts of things, make sure you're focusing on reading the definition, because that's the underlying skill you're practicing here. So someone asks about order of operations for logic stuff, and in particular when negating things. And I would say no, other than that you use parentheses. Okay. So okay, and so for logic and set theory stuff, I would not try to come up with an order of operations. And so as a result, you should never write something like this. This is not a well-formed thing. Okay. Why not? Because I don't know whether to take the intersection of A and B first and then union that with C, or if I'm supposed to take the union of B and C first and then intersect that with A. And I will get different answers most of the time if I do that. Okay. The only time we get away with this is if you have something like A union B union C. We don't have to put parentheses. And the reason we don't have to put parentheses in this instance is it doesn't matter which you do first. But again, this first thing, I should write this, if that's what I mean, or I should write this, if that's what I mean. And then once you have the parentheses, then you know what order to do things in. Okay, someone who's worked, I think, a little bit ahead, because I think this is from the 3.1 videos, asks about, is there a good way to guess how to write something like n cubed plus 1? Because there's a proof somewhere there where it turns out that everything sort of hinges upon the fact that n cubed plus 1 can be rewritten in this way. And so they ask, is there like a good rule of thumb for how to guess this kind of thing? Okay. And the answer is not really. Math is fundamentally a creative exercise. You're going to have to come up with stuff. Okay. But just like any creative exercise, there are certain tools you use a lot. And so you might learn how to paint realistic trees or fingers or perspective or whatever, and then you might deploy those in a lot of different paintings. In the same way, there are certain tricks that you'll uncover with proofs and techniques with these sorts of things as you do them over and over again, where you might be able to use the same tool or the same idea more than once. And so that's something you're doing in this course specifically, is building a tool basket with which to work on these things. Okay. Okay. Someone asks if negation is the same thing as contrapositive, which is an excellent question, and the answer is absolutely not. Negation and contrapositive are not the same thing. So There's a few pieces here, but let me reiterate the pieces. Okay. So piece 1, what things have negations and what things have contrapositives? Okay. Statements have negations. Okay, so remember, what makes something a statement is just that it is well enough defined to have a truth value. That is, it's true or false. Okay, and so as soon as something is a statement, it has a negation. Okay. On the other hand, the thing that has contrapositives are implications. I realize I did not actually write the full sentence here. Sorry. Implications have contrapositives. Okay. And also converses. Okay, so all three of these things are different. Negations, contrapositives, and converses. Okay. So note, an implication is a statement, so an implication also has a negation. Okay. And so an implication has, in fact, three different things. An implication has a contrapositive, it has a converse, and it has a negation. And in general, all three of those things are different. Okay. So remember, implications get written in a bunch of ways, but the most common ones are if-then, or if we're talking about raw logic, that is, if I'm writing it in a truth table, I'll write it that way. Or that. All of these are really different ways to write implications. Okay. And so what is the negation, contrapositive, and converse of P implies Q? Okay, so the negation of P implies Q. Okay. This is always P and not Q. Okay. This is the thing which has the opposite truth value of P implies Q. So if P implies Q is false, what does that mean? That exactly means that P is true and Q is false. And really all this says is P is true and Q is false. Okay. That is, in some sense, the literal opposite of what a contrapositive does, because the contrapositive, which is this very weird thing where the contrapositive of P implies Q is not Q implies not P. This contrapositive has the same truth value. As P implies Q. Okay, so what this is basically saying is that, in a sense, the negation and contrapositive are as far apart as they could possibly be, because the negation has the opposite truth value, but the contrapositive has the same truth value. Oops. Okay. Then last up we have the converse. And the converse, we don't know its truth value. It might be the same as the original implication. It might be the negation. We don't know. Okay. So here, this is an unknown truth value. So pay very close attention when you're given an implication and you're asked something, because you might be asked to write the negation or you might be asked to write the contrapositive. In fact, you'll be asked to do both of those things on the quiz. And those are asking you to do very different things to the implication. Okay. I said a lot. I'm going to pause for a second. Are there any questions about negations, contrapositives, converses, all of these things? Let's see. How do you negate X is in A minus B union C? Okay. Okay, so before I can write out the negation, I have to write out what this means. Okay, and so for X to be in A minus B union C means X is in A and X is not in B union C. Okay. That's just literally the definition of set difference. To be in A minus B union C means that X is in A and X is not in B union C. But X is not in B union C. Well, that just means X is not in B and X is not in C. Okay, which I think happened to be the first part of this question in some form or another. Okay. So before we can even get to negation, we have to rewrite this out in logical operators. Okay. So X is not in A minus B union C means the same thing as X is in A and X is not in B and X is not in C. Okay. So the negation of X is in A minus B union C is X is not in A, or X is in B, or X is in C. Okay, and so that is a very reasonable way to write the negation of that statement. Okay. So the homework defines this word. Is it B union C? Yeah, so X is in B union C means X is in B or X is in C. So X is not in B union C. That's the negation of this. And so the negation of X is in B or X is in C is X is not in B and X is not in C. Do you see where that came from, Seth? See. Someone asked, do you have to state the universal set when you're stating the complement if the universal set is stated in the context? No, you don't have to list what the universal set is when you're stating the answer if it's given to you in the context. Usually, when people are going to be talking about complements, they'll just sort of agree once and for all what the universal set is for purposes of the conversation, and then go on from there. They don't usually repeat it over and over again. Okay, so next up, can we see if statements are true and false without plugging in numbers? And the answer here is sometimes. So the whole idea of proof really is to sort of bypass the whole plugging in numbers thing. And so the idea of proving things is that sometimes you can show something is true without having to plug in literally every number. But how do you know ultimately if something is true or false? Well, before you get to the point of trying to prove it, usually you have to try some examples. Okay. And then there are tons of things where we have plugged in lots of numbers and we still don't know if they're true or false. So this Law of Small Numbers paper that you're reading for Monday, that talks a lot about a bunch of examples of things where you can plug in some numbers and maybe that sort of tells you the answer, or maybe it leaves it a mystery. And so when you get to what do mathematicians actually do, mathematicians spend a lot of time looking at statements and plugging in numbers and collecting data and figuring out what things actually look like. I spent a great deal of yesterday, in fact, plugging in a bunch of numbers to try and guess what the pattern was in some particular thing I was studying. It is a big part of math. So yes, that is... It's sometimes possible. Usually you're going to have to plug some numbers in first to make an informed guess, so that then you can prove your informed guess. Okay. Next, someone asks, and this is a great question, to sort of reiterate the difference between an element and a subset. Okay. So if I have some set, and so the context where this gets a little bit confusing is when the set itself has these sorts of things in it. So what's a subset? A subset is a set all of whose elements are in the original set. Okay, and remember, we quantify this pretty explicitly as A is a subset of B, means for every x in A, we have x's in B. Okay. This quantifier here is just putting into very explicit math this statement, all of whose elements are in the original set. Okay. But in particular, a subset better itself be a set. Okay. So 1 cannot be a subset of anything, because 1 is not a set. Okay, so 1 is not a subset of A. Okay, what 1 is an element of A. Okay. And so when you list a set like this, the elements are just the things that are in the list. So each thing I've just underlined in blue is one element of A. And so when you write down something like the size of A. The size of A in this case is 5. A has 5 elements. These are those 5 elements. So if you're talking about notation here, 1 is an element of A. 1 is not a subset of A. The same thing is true of the set 2, 3. The set 2, 3 is one of the things in A. So this is an element of A. Okay. But it is not a subset of A. Okay. If it was a subset of A, what would that say? That would say that 2 is an element of A and 3 is an element of A, neither of which are true. Okay. If you look at something like 1, 2, 3, this is not an element of A, because it's not in my list. And it's also not a subset of A. And it's not a subset of A because not all the elements of 1, 2, 3 are elements of A. Namely, for example, 2 is not an element of A. And then if you want to muddy the waters as much as possible, 1, 4 is an element of A because it's listed there. But 1, 4 is also a subset of A. But it's a subset of A for completely different reasons. Namely, it's a subset of A because both 1 and 4 happen to be elements of A. So I have written here in green the fact that 1, 4 is an element of A, which corresponds again to the fact that this piece underlined in green is listed. Whereas then 1, 4 is a subset of A because both the elements 1 and 4 happen to be elements of A. Okay, I know this is a frequent source of confusion, but are there questions about this and which to use when and which they both mean? For cardinality, you count each element only once. Sets can never have repeats. So if you write something like A is 1, 2, 3, 2, 1, you've just written the set 1, 2, 3 in a somewhat verbose way. So the size of this set, the cardinality of this set is 3, whether I write it like this or like this. It's the same set. So sets, two things sets don't have. Sets don't have an order of elements. And sets don't have a multiplicity of elements. So by order, I mean the set 2, 1, 3 is exactly the same thing as the set 3, 1, 2. This was relevant on... This was relevant on the bipartition question on the homework, which I can talk about in a minute. Okay. Someone asks if it's grammatically correct to use XOR in a sentence. I am okay with XOR in a sentence. XOR is a word. You can use it in a sentence. Okay. I want to talk a little bit about the bipartition question and a little bit about the doubly even question. But before I talk about those, are there any other things from the homework or lecture or whatever that you would like me to clarify or talk about or anything like that? Okay. So let's talk about these two definitions. And so let's practice just a minute reading the definitions. So I'm going to copy the definitions down from the homework. Sorry, exist even integers. That was the whole point. Okay, so here's our definition. Okay, and so definitions tend to have this structure again, where there's a few pieces. So first of all, there's this linking piece, if, which connects to the definition usually is after the if. So this piece, this is sort of the definition. The thing that's underlined or in italics, but I can't write italics by hand, so I underline it. But the thing that's underlined or in italics, this is the word being defined. And then this phrase at the beginning, where I say something like an integer n, this is telling me what the word applies to. And you'll see almost all definitions in math are written out in this rough form. Okay. And so here when we talk about what the adjective applies to, we're talking about things, or we're talking about what category of things it makes sense to ask the question. So, for example, when I'm talking about even or odd, it makes sense to talk about whether an integer is even or odd. It doesn't make sense to talk about whether a set is even or odd, or a vector, or a complex number. Okay? And so this is sort of the category of things where it makes sense to ask the question, is this thing blank, yes or no? Okay, so in this case, is a thing doubly even or not? It's telling us, okay, that's only going to apply when we're thinking about integers. We're not going to talk about whether circles are doubly even or not. Okay. So that's our sort of structure of a definition overall. So you can get to things like, say, 84 is doubly even. Okay, and why is that? It's because 84 is 2 times 42. And these are both even, so that could be my x, that could be my y. And so I've written 84 as a product of 2 even numbers, and so 84 is doubly even. Okay. Notably, this is not the only way that you could go about proving this. You could also just as easily have written this as 14 times 6, and that would also be a product of 2 even integers that multiplied together to be 84. That would be fine too. Okay. All, again, this there exist quantifier means is that there's at least one way to do this, and there's definitely at least one way to do this. Okay. So then the sort of question I wanted to get your brain thinking about here that a lot of people have asked about was, is 98 doubly even? Okay. And so the answer here is no. And so what I'm really trying to get you to think about here is, how are we going to show that? Because we're trying to be able to sort true statements out from false statements. That's the whole point of the class. So I wanted to get your brain sort of turning about, okay, if this thing is not doubly even, how do I show that? Okay. And so the statement that I'm looking at here is, there exist even integers x and y such that 98 equals x times y. Okay. So I either want this to be true, or I want the negation of that statement to be true. Okay. And so what's the negation of this statement? The negation of this statement would be, for every pair of even integers x, y, we have x times y is not 98. So here's a way you can think about whenever someone says, okay, is this statement true or false? Or they say prove or disprove this thing or whatever. What you can think of them as really being saying is, write out the statement, write out the negation of the statement, and decide which of these two is true. Okay. Because between a statement and its negation, exactly one of them is true. Okay. If the statement's true, great. If the negation's true, that means the statement is false. Okay, and so this could be very helpful. Okay. So let me try and convince you that if I multiply 2 even integers together, I don't get 98. Okay. And so the observation here is that if I multiply 2 even integers together, the result is divisible by 4. Why is that? Well, if x and y are even, that means x is divisible by 2 and y is divisible by 2. So then x times y will be divisible by 2 twice, which will say that it's divisible by 4. Okay. However, numbers that are divisible by 4 are not 98. Hey. And so the underlying logic here, how do you convince yourself that 98 can't possibly be doubly even, is to write out this statement and say, aha, I know this statement is true. This is the negation of the original statement. And I know this is true because the product of two even numbers has to be divisible by 4, but 98 isn't. So that shows me that x times y is not 98. So this is true. The original statement's false. 98 is not doubly even. Okay, I want to give you plenty of time for the quiz, but are there any other short questions we want to talk about, review before today, or before the quiz? Okay, well, with that, I will go ahead and post the quiz on Katie. So you should, sorry, you should now be able to see it. So you can take the next 85 minutes, 75 minutes? You can take the next 75 minutes and go ahead and turn in and write up the quiz and then turn it in. So you should write it up as a PDF in LaTeX. You should make sure, as always, that you proofread it before you turn it in. So you should not have any obvious LaTeX errors in the thing you turn in, because you should have read it again before you turned it in. And then after that, have a wonderful weekend. And I will see you on Monday. Be sure to email me if you have any questions. But from there, have a great weekend. And I'll talk to you later.